You're listening to the Bare Metal Cyber Prepcast, created to help you succeed in your Server Plus certification journey. Learn more at baremetalcyber.com, where additional prepcasts, books, and training materials await. Let's get started. RAID stands for Redundant Array of Independent Disks, and it represents a fundamental storage architecture in server environments. By combining multiple physical drives into a single logical unit, RAID offers improved performance, fault tolerance, or both depending on how it is implemented. In this certification, RAID principles are critical to mastering storage planning, redundancy configurations, and failure recovery strategies. Understanding RAID is not just about technical design, but also about anticipating how a system behaves when things go wrong. Each RAID level offers a unique blend of performance, capacity, and fault tolerance. Some prioritize speed by splitting workloads across drives, while others provide redundancy through mirroring or parity. Technicians preparing for the exam must understand the advantages and limitations of each configuration. The choice of RAID level directly impacts performance metrics, backup strategies, system uptime, and even the cost structure of server deployment. This knowledge is essential when building or supporting resilient infrastructure. RAID 0 is a storage method that uses a technique called striping. In this configuration, data is split and written across two or more physical disks, allowing multiple drives to operate in parallel for improved speed. However, RAID 0 includes no redundancy. If even one drive in the array fails, the entire dataset is lost, since parts of every file are distributed across all drives. Because of its lack of fault tolerance, RAID 0 is only used in environments where performance is valued above all else and data is either non-critical or already backed up elsewhere. RAID 1 provides redundancy through a method known as mirroring. In this configuration, data is written identically to two drives, ensuring that if one drive fails, the other retains an exact copy of the information. While this does reduce available storage to 50%, it significantly increases reliability. Write performance may slightly decrease because each operation must occur twice, but read performance can improve as reads are balanced across both drives. RAID 1 is ideal for small systems where data integrity is crucial and simplicity is desired. RAID 5 strikes a balance between performance, capacity, and fault tolerance. It uses block-level striping like RAID 0, but adds distributed parity information that allows the array to recover from a single drive failure. At least 3 drives are required for RAID 5 to function, and 1 drive's worth of capacity is used for parity. If one disk fails, the parity data and remaining disks can reconstruct the missing content. This setup is commonly used in production environments where cost control and reliability are both priorities. RAID 6 builds upon RAID 5 by introducing a second layer of parity, providing protection against 2 simultaneous drive failures. It requires a minimum of 4 drives, and 2 drives worth of space are reserved for parity. This additional redundancy means less usable capacity compared to RAID 5, but it offers much stronger protection in larger arrays or when rebuild times are long. RAID 6 is particularly useful in high-availability environments where hardware replacement may be delayed or where data loss is unacceptable. RAID 10, sometimes called RAID 1+0, combines the benefits of striping and mirroring. It creates mirrored pairs of drives and then stripes data across those pairs. This configuration requires at least 4 drives and offers excellent performance along with fault tolerance. If a drive fails, its mirror continues to operate, and striping ensures high throughput. RAID 10 can tolerate multiple drive failures as long as they do not occur in the same mirrored pair. This setup is used in systems requiring high performance with robust redundancy. Just a bunch of disks, known as JBOD, is not technically a RAID level, but is often included for comparison. JBOD simply aggregates individual drives into one logical volume without any striping, mirroring, or parity. Each drive functions independently, and data is stored contiguously across drives. While JBOD offers full use of total capacity, it provides no fault tolerance. If a drive fails, the data stored on that drive is lost. JBOD is commonly used in lab environments, experimental setups, or where redundancy is handled by other means. Performance varies significantly across RAID levels. RAID 0 offers the highest write and read performance because it stripes data without overhead. RAID 10 also performs well due to its combination of striping and mirrored access. RAID 5 and 6 introduce computational overhead due to parity calculations, which slows down writes more than reads. JBOD performance depends entirely on the individual drives, without any aggregation advantages. Selecting a RAID level often involves weighing speed against reliability. Different RAID levels offer different levels of fault tolerance. RAID 1 allows for recovery from a single drive failure by using mirrored copies. RAID 5 also tolerates one failure using parity. RAID 6 tolerates two simultaneous failures, while RAID 10 can tolerate multiple failures as long as no mirrored pair is fully lost. RAID 0 and JBOD do not offer any fault tolerance. When failures occur, successful rebuilds depend on healthy parity data, intact disk controllers, and well-documented array configurations. These factors affect recovery time and system availability. Storage efficiency is a key consideration in RAID design. RAID 1 uses 50% of total drive capacity because each disk has an identical mirror. RAID 5 offers better efficiency by using the capacity of N-1 drives for data. RAID 6 reserves 2 drives, worth for dual parity, resulting in N-2. RAID 10 also uses only 50% of capacity due to mirroring, but compensates with excellent performance. JBOD uses 100% of available space but offers no protection or performance benefit. The efficiency must be weighed against risk tolerance and budget. For more cyber-related content and books, please check out cyberauthor.me. Also, there are other prepcasts on cybersecurity and more at baremetalcyber.com. Each RAID level has a defined minimum number of drives required to function. RAID 0 needs at least 2 drives to implement striping. RAID 5 requires 3 or more drives to accommodate both data and parity. RAID 6 needs a minimum of 4 drives to support dual parity protection. RAID 10 also requires 4 drives combining mirrored pairs with striping. The exam includes questions on these minimum requirements to test readiness for real-world deployments. Selecting fewer drives than needed will prevent array creation or result in a degraded configuration. RAID can be implemented through hardware or software, and the differences between these two methods impact performance, cost, and flexibility. Hardware RAID uses a dedicated controller card that manages the array independently of the operating system. These cards often include battery backup and caching to enhance speed and reliability. Software RAID is managed by the operating system itself and consumes CPU resources to perform RAID tasks. While software RAID may be more cost-effective, it often lacks advanced features and may introduce latency under load. The exam includes scenarios that require evaluation of these trade-offs. Some RAID configurations allow for hot spare drives to remain on standby within the system. A hot spare is a drive that is powered on and connected but not actively used in the array until a failure occurs. If a disk in the RAID fails, the controller can automatically begin rebuilding the array onto the hot spare, reducing downtime and risk of data loss. This feature is especially important in environments where administrator intervention may be delayed. The certification includes the concept of rebuild readiness and proactive redundancy planning. RAID controllers come with a variety of interfaces and built-in features to support diverse deployment environments. Common drive interfaces include Serial ATA, Serial Attached SCSI, and Non-Volatile Memory Express. Advanced controller features may include write caching to improve performance, read-ahead to optimize sequential access, and online capacity expansion to grow the array without downtime. Management interfaces include pre-boot BIOS utilities, command-line tools, or web-based graphical user interfaces. Familiarity with these tools helps technicians manage and maintain arrays effectively. Every RAID level comes with its own set of limitations and trade-offs. Configurations with higher redundancy, such as RAID 6 and RAID 10, require more drives and reduce usable space, increasing cost. Parity-based RAID levels like RAID 5 and 6 often suffer from reduced write speed due to parity calculation overhead. Rebuild times also increase as total capacity and drive count grow, especially for large arrays or slower disks. Understanding these constraints helps ensure that RAID is selected and tuned appropriately for workload and reliability needs. Monitoring the health of a RAID array is critical to preventing data loss and unplanned downtime. RAID controllers and operating systems typically provide diagnostic logs, real-time status indicators, and automatic alert systems. These alerts can include predictive failure warnings, temperature anomalies, or parity inconsistencies. Setting appropriate thresholds and reviewing logs regularly are essential practices covered in the certification. Proactive health monitoring ensures that faults are detected early and resolved before data loss or performance degradation occurs. Maintaining accurate documentation of a RAID array's layout and settings is essential for recovery, migration, and compliance. Technicians should record the RAID level, disk order, controller settings, hot spare assignments, and any special caching or performance features in use. This documentation helps rebuild arrays after hardware failures, move configurations to new systems, or audit storage practices. Server environments that lack clear documentation often face extended recovery times and increased risk during maintenance. RAID is a foundational technology for server performance and resilience. Its correct implementation ensures continuous access to data, balanced storage workloads, and streamlined recovery in case of drive failure. By understanding how each RAID level functions, what hardware is required, and how to monitor and document configurations, technicians can build robust storage solutions that meet business needs. The next episode explores hardware RAID versus software RAID in greater depth, including configuration interfaces and real-world use cases. Thanks for tuning in to the Bare Metal Cyber Prepcast, your trusted source for cybersecurity news and insights. Remember to subscribe at baremetalcyber.com so you never miss an update. And visit cyberauthor.me for best-selling cybersecurity books that equip you with expert knowledge. Until next time, stay secure and stay vigilant.